turn. Full screen, yeah? That would be right. Yeah. Okay, so I will show recent results on kaon physics from OKA experiment. OKA is a collaboration of Institute for High Energy Physics, Institute for Nuclear Research, and Dubna, GINR. The talk layout is first I will show some details of our beamline, detector, data, and then there will be three topics: is search for axion-like particle in this decay, then study of radiative K-2 decay and measurement of difference of vector and axial vector constants, and finally study of the radiative K-3 decay. So OKA is working in the RF separated K plus minus beam. It has enriched fraction of kaons in the beam. Normal fraction is say 1.5%, and we have 10 times more kaons in the beam. And separation is achieved by use of so-called Panofsky scheme, which includes two radio frequency cavities, which oscillate with very high frequency, is so-called S-band, and they provide declination of particles in the vertical direction. And the idea is that you have some phase shift between these two cavities, and they shift the tune in such a way that unwanted particles, pion and proton, get finally after two RF cavities, they get no declination, and they are absorbed by beam stopper. And kaons, as they have different time of flight, they do have declination, and they bypass this absorber. So this zero declination for pion and proton happens at some momentum of the beam. It's around 10, around 13, and around 18 GeV. So we are working with the highest beam momentum. So the parameters of the beam are presented here. We have about 500,000 kaons per cycle of U70 accelerator, and here is this scheme of our beamline. You see, it's rather complicated. So OKA is using this beam, and OKA is a magnetic spectrometer. It includes beam spectrometer, where you measure the direction and momentum of the beam, and also tag kaons with two Cherenkov counters. Then there is decay volume. It has about 10 meters length. The decay volume has a guard system to veto this particles, high angle particles. Then there is a magnetic spectrometer for for decay, for charge decay products. It is on the base of large area proportional chambers and drift tubes. Then there is electromagnetic calorimeter. Another one for large angle photons is just after the decay volume, and there is also hadron calorimeter and muon counters to identify muons. So we use some very simple triggers. It's almost minimum bias, but it with some extra requirement of energy deposit in the electromagnetic calorimeter. So we have rather long history of beam taking. We had runs starting from 2010, and the last one was 2018. And still we hope for some more runs. And the amount of kaons which passed through the setup is 5 times 10 to the 10. So main directions of data analysis are listed here, is quite a lot, and I will concentrate on fresh ones which are not yet published. It's actually I will talk about these three. The last one is I think I will not have time to discuss that. So this is some pictures, a general view of the OKA setup. It's some chambers after magnet. This is guard system during fabrication, which is guard system around decay volume. So this is our second RF cavity. What you see is actually a cryostat. I forgot to say that we are using superconductive cavities, which are cooled by superfluid helium. So it's quite high tech in the beam. So this is a tail of the beam, and here you see a liquid helium distribution system. So first topic is search for axion in the decay to pi of kaon to pi plus pi 0 axion. It's actually so-called axion-like particle. I will explain what does it mean. So in QCD, axion is a hypothetical particle which is invented to wash out CP problem in QCD. Its properties are described by just one constant, f sub a, and for example, the mass of axion is proportional to pi in mass and to ratio of f pi to this f sub a. The axion has decay to 2 photons. Lifetime is also defined by Fa. It's proportional to the Fa to the 5th power. And if axion is considered as a dark matter candidate, it has to have lifetime more than lifetime of the universe, and from that you can derive that the mass of the axion should be less than 10 eV. And axion-like particle is a bit wider concept, which assumes that axion may get mass not only from QCD but from other mechanisms. And then in this series you have 2 independent parameters: the mass of axion-like particle and this F. And in this way, from similar requirement, you may have softer limit for the mass, which is less than 1 JeV. So we're working in this constants, in this concept. So it's axion, but with mass which is allowed in kinematics of this decay. So axion may have couplings to SD, FCNC, and as axion should have derivative coupling because of so-called shift symmetry. It couples through vector or axial vector couplings, and so this is a diagram of this decay, and as parity is conserved in QCD, the decay of K plus to pi plus axion probes vector coupling, and this decay, which is under study, is sensitive to the axial vector coupling. Then the matrix element can be related through isospin symmetry to the matrix element of K plus to pi plus pi minus, and this is known from KL4 decay. There are three form factors which are measured. You can find them in PDG, and so actually we have very good model for this decay. And for example, branching depends just on FSDA. So it's inversely proportional to the square of this constant. So our Monte Carlo is a very detailed one. So the selection is rather straightforward. First, we select pi plus pi zero system, and this part of selections is common for this decay under search and K plus pi zero decay, which we use for normalization. So okay, I will not describe the details, but at the end we have 45 millions of K plus pi zero decay. So this selection of pi plus pi zero and pi plus pi zero and axion differs in just last step, because for this decay we of course assume that there is energy conservation, and for this decay we should use extra cut on missing energy. So contrary require that there must be some missing energy of more than 3 GeV. Okay, there is quite a lot of backgrounds for this decay. Here they are listed, and we should have extra cuts which kill these backgrounds. So, for example, okay, to kill K-3 decay, you should veto muons by requiring no signal in muon counter. So Ke3 is killed by using E over P cut. And okay, we should have identification of pi plus, and this is done by using GAMS electromagnetic calorimeter and hadron calorimeter. Okay, and the last cut is a requirement of absence of signal in guard system. So after that, we suppressed after this suppression of backgrounds, we still have some, and they are seen in the Dulles plot. The parameters of the Dulles plot are pi plus pi zero mass squared and pi plus axion mass squared. So here is signal Monte Carlo for 3 different masses of axion, and here are backgrounds from background Monte Carlo. So, and you see we are lucky because we can sacrifice, say, half of signal, so select only this upper blobs, And by this cut, we very strongly suppress the remaining background. So after this Dalitz plot cut, we get this kind of distribution over missing mass squared. It's presented here in logarithmic scale and in linear scale. So this is missing mass squared. And you still have, you see some background. You see here is 20 events. So it's already small, but still there. So this peak is due to pi plus, pi zero background. So pi zero escapes somewhere. It's strongly suppressed by a factor of 10 to the 5 roughly, but you see not completely. And this background shows how the signal actually should look like, because it's missing mass, yes, squared. So, for example, if you would have a similar peak here or here, is a great discovery. So one background is, which is in yellow, is this pi plus, pi zero, and another one, for example, this blue line, is remaining K-3 background. It's mainly works in non-physical region. You see here is negative missing mass squared, but still it has tail to the positive region, and for example, it affects the limit for zero mass of axial. So you see that there is no extra signal, at least strong one. So we can put upper limit on the branching of this decay, and it's done by adding to the fit model of the width of the single we know from Monte Carlo, and here you see how this fit looks like when it's it's actually applied to the difference of this plot, difference when you subtract background. So this background free distribution, and you see how the fit is working. So finally, we get upper limit for the branching of K plus to pi plus pi zero axion, depending on mass of the axion. So you see the scale, it's 10, here is 10 to the minus 5. This is 10 to the minus 6 and 10 to the minus 7. So this corridor is systematic errors, and as I mentioned, from this upper limit on branching, you can derive lower limit for effective constant FSDA. This limit is this constant has a dimension of Jev, and you see it's in the most interesting region of low mass. It has a value of 6.5 10 to the 7 Jev. So this is actually our main result. So it's interesting to compare with existing limits. They are presented here. It's taken from this paper, and you see there is just one limit from K plus pi zero axion. It's old Brookhaven paper, which actually was not dedicated to this search, but it's kind of byproduct, and they got 1.7 10 to the 7. So we significantly improve this limit. Other limits are from hyperon decays. You see them here, And the best one actually is from neutral kaon oscillation, is from epsilon k. So it's 4.4 10 to the 7. So you see our limit is best from among this high energy physics experiments. Okay, there is actually limit from astrophysics, from say neutron stars formation when there is a supernova explosion. The neutral stars is formed, and inside this neutron star there may be a decay of lambda to neutron axion. And by measuring energy flow, you can derive a limit. And limit actually is very good, is say more than 10 to the 9 GeV, but it's strongly model dependent. So, okay, it's okay. So that is all for axion search. So another topic is devoted to study of radiative decay, radiative K μ2 decay. So the story here is that when you study radiative decays, you always face with two types of diagrams. First one is so-called internal Bremsstrahlung, when photon is emitted by charged particle in the initial or final state. And another one is so-called structure-dependent diagrams, when photon is emitted by some virtual particles in the decay. So, of course, this is of great interest, because this is okay. This does not give you new information about physics. So, as a result, the density on the Dalitz plot, x and y is proportional to energy of photon and energy of muon in the central mass of K. And you have these three terms. First term is pure IB, is this diagram squared. Another one is pure structure-dependent term, which is this diagram modulus square. And there is also interference term. And this SD and int depend on vector and axial vector form factors. You see how they are used here is a sum of this form factors and difference. The corresponding terms are called SD plus, SD minus, and int plus and int minus. And this decay is interesting because it lives on the borders of the Dalitz plot. You see, so IB lives in this corner, int minus lives on this border, SD plus here, etc. So after some study, we realized that we have some chance to catch this int minus. So we studied Dalitz plot in this region. There is quite strong backgrounds. The main one is from K μ2, when one photon is lost by pi zero. There are some other background, but this is the main one. So the previous history of studying of this decay is that it was studied actually, the best paper with highest statistics is our paper, but when we were working on our previous setup, it was called ISTRA Plus. So the paper was published in 2011, and you see the statistics is okay, 22K, and we measured it provided first measurement for this difference of vector and axial vector constants. So our task is to increase the statistics and to lower this error in this parameter. Okay, so there is some selections, of course, but they are very simple because the final system is rather simple. You select one charge track in the final state, identify it as muon. Then we should find shower in the electromagnetic calorimeter and require nothing in the guard system. So of course, after that you have still a lot of background, and Dalitz plot is divided into strips, in X, and X, if you remember, is proportional to the energy of photon in the CMS. So the step of the strip is roughly 10 MeV in energy of photon. So then we have background and signal. We know the shape from Monte Carlo, and we do a fit. So we find number of signal events in every strip, and you see the discrimination parameters are first this distribution over Y, so over energy of muon. You see this signal peak and background. The main one, as I said, is KM3. Then another parameter is cosine of angle between muon and photon. Everything is in rest frame of kaon. Also, you see difference between signal and background. And the last one is the invariant mass of all the system of muon, neutrino, photon. It's calculated, of course, assuming zero mass for neutrino. So actually, we could fit only this histogram, yes, and to use it to obtain number of signal events. But we are fitting all three histograms to get more information, yes. So finally, what we have is number of events in every strip, and we divided to the Monte Carlo, and Monte Carlo in this case is pure IB, so no structure-dependent terms in the Monte Carlo. So if there would be no interference term int minus, we would have constant, just one. But you see, we observe not a constant but falling distribution. You see, the scale is not from 0; it's 20%. It's 20% fall of distribution, and this is actually observation of interference, observation of int minus term, and you can fit it also and find difference of FV and FA. Actually, fit gives you the value 0.135. So it should be compared with predictions of chiral perturbation theory, which gives 0.054. So you see, it's quite different. It's almost 3 sigma difference. These form factors are calculated not only in in this order p to the 4th, but also in the next order, p to the 6th. And there they depend on x. And actually, we also made a fit. And the theory point is out of 3 sigma ellipse. So the conclusion is that we do see a difference, significant difference between our measurements and chiral perturbation theory. But fortunately, there are other calculations. There are other calculations. For example, in the lattice, there are lattice calculations. It's rather paper, and they predict smaller difference of vector and axial vector constant. Still, there is difference, but it's only 2 sigma, so it's not so bad. Okay, so roughly it's everything about this decay. We expect doubling of statistics at the end of next year, and hope to clarify the situation here. So now I'm coming to the last decay. It's radiative K-3. It's also interesting because first you have 4 particles in the final state, so you can construct CP-odd correlation. It's a mixed product of the vectors of photon, lepton, and pion, and so it's one reason why it's interesting. Another one is that there are quite precise calculations in chiral perturbation theory. It's again in order p to the 4th and p to the 6th, and they predict branchings, and also predict some CP-odd asymmetry, but due to CAD final state interactions. You see this asymmetry is rather small, which gives you room to search for new physics. So this is also interesting. So previous history of study of this decay is listed here. It's taken from PDG. And again, the best statistics is in our previous paper when we were working on ISTRA plus setup. And you see, this is a rather rare decay. It's branching is around 10 to the minus 5. And we had only 153 events in this paper. So our task was to increase the statistics. And okay, we make some event selection. They are listed here. I will not lose time. They are more or less straightforward. And after the selections, you have this picture. This is again invariant mass of all particles in the final state, assuming mass of neutrino 0. And here are backgrounds. The blue is K-3 background. Green is radiative K pi 2, and red is K pi plus pi 0 background. The most important is actually the most troubling, I would say, is this green, which is radiative K pi 2, because it has tendency to peak at the same place where the signal is located, and this is because pi plus can decay to muon neutrino, and then it's indistinguishable from the signal. So if you subtract background, you see this clear peak, which is in agreement with Monte Carlo, and we have around 1,000 events. So we significantly increase the statistics. Here we are using extra cut on energy of photon. We require that it should be more than 30 MeV, because otherwise, here is its energy spectrum. Otherwise, we have severe background at smaller energy, as we have to cut at 30 GeV. So the limit from above is to compare our branching with previous results. Actually, theory is using is not using this upper limit. Instead, it's using some cut on angle between muon and photon, and we actually have to do the same to compare with theory. So there are predictions from theory, as I said. So the branching calculation is straightforward. We're using K-3 for normalization. Here is distribution over invariant mass of muon pi zero neutrino. You see it's a logarithmic scale. You see we have quite good description of data by Monte Carlo, and we have 4.5 millions of events. So this and you see the background is rather small. So we get first the ratio of branchings of radiative K-3 to K-3, and then using PDG value for branching of K-3, we can calculate branching of radiative K-3. Here is the result, and with this cut, it's 1.5 times 10 to the minus 5. And as I mentioned, to compare with theory, we should use a bit different cuts, and then branching is 2 times 10 to the minus 5. So you see that it's in good agreement with actually with all theoretical calculations. We have some extra distributions. In particular, this distribution over Xi. Unfortunately, a background also, of course, also have peak in the same region where we have effect. And after subtraction, we have this distribution for the signal, but its result is affected by increasing of errors. Yes. So in future, we hope to somehow to suppress stronger the background to avoid this effect of losing accuracy. So you see there is no visible asymmetry over this in distribution over this over Xi, and asymmetry, which is defined as number of events above zero minus number of events below divided on the sum, is measured to be this actually zero, but what is important is error is plus minus 0.007. Say. So it's not too good, but this is present status. Another important distribution is distribution over angle or cosine of angle between muon and photon, and you see that this is quite well described by the Monte Carlo. And Monte Carlo has inside this chiral perturbation theory of p to the fourth. Okay, so it's actually the end. I think I am on time. And here is summary, but summary you can just read it. Is just repetition of the results which I has shown. Thank you.
Thank you very much for nice talk. Please, questions first from online audience. Switch on the microphone.
Yes.
Please.
The talk was really very interesting, but the question is not related to OKA experiment. To our knowledge, there was recently interesting proposal by one of the members of the OKA collaboration, experimentalist Samolenko, and also by Likhadev and Petrov, to think about using strong K+ beams in studies with multi-quark systems in interactions with protons at protovinol. Is there any chance that this project may be realized in the future?
Okay. I can show you in the very beginning of the talk, I showed the main directions of our research, of our analysis, and there you can see we do have one result using target. Yes, it's not K and decay, but it's interaction of K, and it's K+ to copper, actually to copper nuclear, and in the final state you have K+ pi0 copper. And to realize this reaction, we put very narrow thin target inside the decay volume. Yes, and here we got some very interesting result. We see the effect of chiral anomaly. So this is a rather specific reaction. It's actually at very low T. It's and there is so-called Primakov effect. Yes. So, but this I show to demonstrate that in principle we have already started this kind of spectroscopy. But for the subject you mentioned, we need strongly change the setup because we should have
understanding. Okay.
Yeah, but it's possible. It's quite possible. So we have that in the plan. In our original plan, we mentioned that finally we will be doing spectroscopy.
Okay, very interesting. Thank you.
Thank you. More questions from the audience?
In the case of the last decay, K to pi0
K-3.
Can you compare with some parameters of chiral perturbation theory, which you confirm by the agreement with theoretical predictions?
I mentioned that we have in our Monte Carlo we have implemented this chiral perturbation theory results in p to the fourth. It's actually this paper was done by theoreticians, and they provided code. Yes, what it was very nice. It's not just formula, but they provided
only code.
Not yeah. So we also we using their code. Yes, but okay, and you see that agreement is not bad. Yes, in
Yes.
this energy spectrum, and what is also important in this cosine. Yes, in cosine we have very good agreement. So the conclusion is that we do agree with perturbation theory in p to the fourth at present statistics, at least. Yes?
Understand. And you also agree with the results of by Bayesians.
Yes, but in only in branching. Yes, we don't compare other distributions because
And it may be interesting to compare the parameters that maybe Bayesians used. It is interesting to set limitations on parameters that the
I see,
people
yes.
use in this
Okay,
field.
we can do that. Yes, in future probably probably it's better. First, it's better to do in similar decay, but where is electron instead of muon, because then we have done this study. Probably the answer to the question is in paper about radiative K3, and actually this one complements this study, and this has much higher statistics. We have I think 50 Ks of this decay. So there, the detailed comparison is possible.
Thank you.
If there are no more questions, I do not see, then let's thank Obraztsov once again, and
Thank you.
take all this session, and we meet at 4:40 after coffee break.
Так.